Hello to all fans of physics and physical experiments. This is Andrei Shetnikov with you, and our video today will be dedicated to equilibrium in electrostatic, that is, time invariant electric fields, or to be more precise, the impossibility of such equilibrium. And although this question was already discussed at the end of the video dedicated to Gauss's theorem, judging by the comments on that video, this topic requires a closer look, which is exactly what I will do now. And I will begin this discussion with Earnshaw's theorem in its simplest formulation, which states that it is impossible to create a stationary electric field in which an electric charge placed at some point will be in stable equilibrium. That is, with any small deviation from this equilibrium position, the electric forces acting on it would return it back to this equilibrium point. And the fact that this is impossible is proven using Gauss's theorem. Indeed, let us suppose that this is possible. Well, then we surround this charge with a small sphere in space, and at any point on this sphere, the force acting on the displaced charge must be directed inward toward the center of the sphere. This means that on the entire surface of this sphere, there is an electric field directed inward. But according to Gauss's theorem, the flux of such a field must be equal to the charge enclosed within the sphere. But there was nothing inside the sphere. Well, except for our test charge, which we placed there afterward in this field. And we arrive at a contradiction. On the one hand, there is a non-zero flux directed inward through the sphere, but on the other hand, there is nothing inside the sphere, so the flux should be zero. Therefore, it is impossible to create such a field, and thus it is also impossible to balance the charge. Thus, I want to emphasize once again that my reasoning was local, concerning the equilibrium point and a certain small neighborhood around this point. But some people write, your reasoning was about electrostatics. But suppose we add gravity, and then perhaps we can balance a charged body on which the force of gravity mg acts downward and the electrostatic force E times Q acts upward. These forces balance each other, and in this case, the equilibrium is stable. Now I will show that this is also impossible. Indeed, let's take the gravitational force mg and replace it with an equal force, acting in the same direction, exerted on the same charge by another uniform electric field. So that this field E is equal to mg divided by q. And then we've reduced everything to the previous case. There is no gravity, but there are only electric fields. And we know that equilibrium in such fields is impossible. So unfortunately, it is also impossible to suspend a charged body using some external charges so that they support it from below. But of course, there are also inventors who tell us, we don't believe in your mathematical physics, that's all orthodox science. We'll take a torus, place it horizontally, charge it, and then somewhere above this torus it will be possible to suspend the charge, because the forces from different parts of the torus, let's say, act on this charge along a cone like this. And then they will balance out the force of gravity, and everything will remain in equilibrium, stable equilibrium at that. But these people are mistaken, unfortunately, and now we will demonstrate this, not with the general theorem, but by analyzing the force field created in this way. Here I have schematically drawn a cross-section of the torus and its axis of rotation. First, let's examine the force field along these axes. Far from the torus, its influence weakens, and there the gravitational field prevails, directed downward. We want the gravitational force at a certain point on the axis to be balanced by the repulsive force from the torus. In that case, below this point, the total force must be directed upward. And this means that further down the axis, there is another point where the total force is zero. Now we need to move away from the axis of rotation. And we'll start by noting that near the torus, the repulsive force from it is strong. And here, the gravitational force can be neglected. So, how is the force field arranged throughout the entire space? The field lines coming from far above will flow around the torus and go downward. One of the field lines emerging from the torus will reach the lower null point on the axis of rotation, dividing the flow into two parts. And both of these parts will eventually go downward to infinity. And near the null points, the field lines will enter these points from some directions and exit from others. No stable equilibrium is observed here. Alas, alas. So I tried to depict something like this in the Volstadt program, but the separators passing through the null points of the field are drawn rather poorly here, so I had to add them in manually myself. And here we are dealing with a characteristic field configuration near a null point, which physicists in their jargon call a DCF double conical funnel. And if this were not a torus, but for example a charged hemisphere, above it there would be a null point where the electric field balances the gravitational field and the force field would be locally arranged in exactly the same way. Here it is important to emphasize another key point. Gauss's theorem, which we use when proving Earnshaw's theorem, is equivalent to Coulomb's law, according to which the force of interaction between point electric charges decreases in inverse proportion to the square of the distance. If Coulomb's law did not hold, Gauss's theorem would not hold either, and our proof of Earnshaw's theorem would no longer be valid. Moreover, a counterexample can be given here. Suppose that the force of interaction between charges decrease not in inverse proportion to the square, but to the cube of the distance. With the square of the distance, if we take a uniformly charged sphere, the field inside this sphere will be zero. But if the force decreases as the inverse cube of the distance, then the field inside the sphere will no longer be zero. It will be directed from the walls toward the center, and such a field would drive any charge placed inside the sphere, though, of course. This is an imaginary and unrealizable situation toward the center of the sphere. And if we also add the gravitational field, then this charge would shift downward and be held in that position. And, of course, everything that has been said here applies to the equilibrium of charged bodies in stationary fields. As for equilibrium in electrostatic but varying fields, we will discuss that separately and make a special video about the quadrupole trap. For now, please leave your comments, ask questions, and thank you for your attention.